So now that we know what the complex exponential and the principal complex logarithmic functions are and how they operate, what are their mapping properties, I want to take a brief diversion into how some people have used those functions to do some artistic work. In particular, we're going to, in this video, kind of look at how the mapping properties of the complex exponential function can help us to turn one type of artistic drawing into a different type that's a little bit more interesting. And in particular, also how we can go backwards. So this is a little bit self-serving, as you'll see in just a moment, but it's a really cool artistic application for how the mapping properties of these complex functions actually have some interesting real-world application. So again, I want to start by just reminding ourselves how these mapping properties work. So the complex exponential function, one of the jobs of the complex exponential function, is to turn vertical lines into portions of circles. And the radii of those circles are just e raised to the x coordinate of my vertical line. So it turns vertical lines into portions of circles. And it also turns horizontal lines into rays emanating from the origin. And if you sort of stick those two things together, we can also show that it turns rays emanating from the origin into spirals going in towards the origin. And that is actually where our story of applications picks up. So it turns out that M.C. Escher, who was a brilliant Dutch artist who also worked very closely with some of the most notorious mathematicians of his day, made a lot of very richly intricate diagrams and woodcuts that involve a lot of he played around a lot with tessellations and tilings and patterns. And some of those patterns have this sort of spirally property to them. So this, for example, is an image of the woodcut that's called Path of Life 3. This was done in 1966. And it sort of depicts these fishy, birdy-looking creatures, some of them black, some of them white, following these red paths. And those paths sort of seem to diverge outward toward the boundary, and then they swoop back inwards, and there's this point at the middle of the diagram that all the red paths seem to be converging onto. So Doris Schatzschneider is a mathematician that sort of first looked at this image and figured out that actually those red paths in Path of Life 3 are indeed spirals, and they're not just any kind of spirals, they're the logarithmic spirals that we would see in this diagram, right? The images of rays emanating from the origin in the complex plane. That explains where these red curves in Escher's Path of Life 3 woodcut are coming from. And so what that ought to mean is that if we understand the complex logarithm function well enough, we should be able to unspiral those spirals. If we apply the complex log to the spiral on this graph, we should get the ray through the origin, the straight line through the origin that we have in the pre-image. So the question is then, what would happen if we applied that complex logarithm function to Escher's actual diagram? If we were to do that, it should answer the question definitively of, did Escher actually sketch logarithmic spirals on this diagram? And is there a regular planar tiling of these black fishbird-looking things that underlies that geometry? So this is what I call the hidden geometry of Escher's Path of Life 3. And I mentioned this was kind of self-serving a while ago because this is a paper that I wrote together with Heidi Burgel, who is a colleague of mine at BSU back in 2012. This is an open access article, so I will put the link to it down in the comment section. You're more than welcome to read it. It's written to be pretty accessible. Journal of Humanistic Mathematics publishes kind of these mathematical research papers that are of a general interest to people in the humanities. So this is a perfect example of how mathematics and art are kind of converging. And sure enough, when Dr. Burgel and I took Path of Life 3 and we ran it through the complex logarithmic function, what popped out, so going kind of from right to left on this diagram, is a regular planar tiling, a tessellation of black fishbirds. And the red curves, which we saw on the original Path of Life 3, indeed did straighten out into straight lines, sort of these oblique straight lines intersecting one another in this version of the complex plane. And so one of the neat things that this does is it gives us a recipe to make our own Path of Life 3 style diagrams. If I have any planar tiling, any planar tessellation that I want to, I can apply the complex exponential function to it to get a new tessellation that spirals in toward the origin in the way that Path of Life 3 actually does. So this is application number 1. Application number 2 takes a different Escher diagram and tries to apply the same idea to it. So this diagram is sphere surface, sometimes called sphere surface with fishes. It's actually a little bit older. It's 1958, so this predates Path of Life 3 by 8 years. And what's different about this is that it sort of depicts what looks like a spirally pattern that's no longer on a flat surface, but is on the surface of a sphere, as the name of this seems to suggest. And it still kind of has the same black and white fishbird looking things following those spirals. But because it's now on this sphere, and the sphere is kind of tilted, there's a little bit more work to do to try to disentangle whether or not the same thing is happening here as was happening in Path of Life 3. And so, yet another shameless plug. This is 2 years after Dr. Burgel and I did the Path of Life 3 paper. I did an undergraduate research project with James Marcotte. So this was an Adrian Tinsley Program summer research grant that allowed us to do this, to take this sphere surface image and apply enough transformations to it that could render it, sort of put it on the same footing as Path of Life 3. This article, too, was published in the Journal of Humanistic Mathematics, which is open access, so I'll put this link down in the chat as well for you. And we found out that, indeed, the same principle applies to sphere surface. It just has these more steps, which were necessary to kind of take the flat perspective image in the original M.C. Escher's sphere surface and figure out what, in a flat plane, that this would end up looking like. So we had to kind of take the perspective out of it, and that's what these first few projection steps were. But by the time we took the perspective out of it, we got this part D here, which is sort of a spirally looking flat black and white fishbird tiling that looks an awful lot like the tiling that was in Path of Life 3. And sure enough, when we apply the complex logarithm function to that, we get a regular black and white tessellation, regular tiling of the complex plane. And again, just like with Path of Life 3, this would give us a way of creating our own custom versions of the sphere surface image, just by taking any regular tiling and hitting it with the exponential function to go from right to left on this diagram. And then you can add the perspective back in and kind of make your own version of sphere surface as well. And just to give you a sneak peek into my office here at Bridgewater, this thing up on the wall was created at the end of these research projects where we sort of took our own tilings, whatever we wanted, and created new Escher-like images with respect to them. So what we see here is actually a version of Path of Life 3, Escher's original Path of Life 3, that instead of having a hexagonal six-fold symmetry, has a five-fold symmetry. Instead, we just had to take the planar tiling and change its scale a little bit so that when we hit it with a complex exponential function, the new period, the new rotational period in the diagram, repeats every 2 pi over 5 angle instead of every 2 pi over 6. So this is a really cool application. It's self-serving, but these were really cool projects that I worked together with a colleague and with an advanced undergraduate student on. I believe that James has now also moved on to be Dr. Marcotte, finished his PhD, and is also in the professoriate today. So really cool project. I'm going to link some resources down in the chat, and it's all powered by the complex exponential and logarithmic functions.